Okay, so we've talked and reviewed about pKa's, understanding equilibrium, but let's talk about how structural factors can influence acidity. We've already talked a little bit about how structural factors influence polarity, which is important for this. But how does that influence acidity? So there are four structural factors that we want to look at and their influence on the acidity of a proton. Remember, we're still talking about protons because we're talking about this in terms of the Bronsted-Lowry theory. So the strength of the bond between the proton and the acid that's being donated and the rest of the acid, that actual bond is going to be considered. The electronegativity of the atom from which the proton is lost. So this is the electronegativity of the atom that's connected to the proton. The electronegativity of the atoms near the proton is also important. So the ones that are close to the proton but not actually directly connected to it. And lastly, the resonance stabilization. So how resonance can potentially stabilize the conjugate base form is important for understanding how acidic something is. So when we compare two acids, if you want to compare and decide what is going to be more acidic, just based on its structure, we're going to use this list and focus on these factors to compare them. So again, the first factor is how strong the bond is between the proton and the acid. So the actual direct bond. One of the influences here is actually the size of the atom that is connected to the hydrogen. As the size of the atom increases, you actually kind of weaken that bond. You weaken the bond between them as the size increases. It pushes away the proton. And this causes the acidity to increase. Remember, again, in the Bronsted-Lowry theory, acidity, an acid, donates the hydrogen. So it actually has to get rid of the hydrogen. So if you make this bond very weak between the acid and the proton, it's more likely to donate that proton. So again, the bigger the atom connected to the hydrogen, the stronger the acid. And it's because we weaken that bond. Now, as you make the atom next to the hydrogen more electronegative, you're going to increase how polar this is. Remember, this is going to increase how much electron density is going to occur on this bond. Now, again, we're just talking about the bond between the hydrogen and the rest of the acid. So just that bond. The electronegativity here, as it increases, as electrons are moved more and more onto the atom connected to the hydrogen, we will also increase the strength of the acid. This is because it's another way to weaken this bond, right? We're moving electron density to the electronegative neighbor. In this case, for water, it'd be moving to the oxygen. Here's the more electronegative atom. Nitrogen is electronegative, but it's slightly less than oxygen and much less than fluorine. And carbon, compared to hydrogen, still electronegative, more electronegative, but again, the electronegativity is less so. And you can see as you make the partner more electronegative, we're going to increase the strength of the acid. Now, I want to point something out between this slide and this slide. we're talking about electronegativity here and size here, and they kind of combat a little bit. So when talking about the partner directly connected to the acid, you have to think of these, keep these both in mind. So electronegativity is important when comparing something that's more electronegative attached to the proton, but size is also important. So if we look at the electronegativity here, if you remember, fluorine is actually more electronegative than iodine. And yet iodine forms a stronger acid, and that's because of the size of the atom here. So these can kind of combat, and I want you to just remember to use these rules in tandem, particularly, again, in this case, where we know that fluorine is very electronegative, but it is smaller when compared to iodine. So this is all about in relative nature and comparison. Okay, another rule and factor to keep in mind is called the inductive effect. And this has to do with the electronegativity of atoms that are not necessarily connected to the proton, but they have an effect on the acidity of that proton. So as nearby electronegative atoms increase, the acidity still also increases. So we know that if you have an electronegative atom directly attached to that proton, it will increase the strength of the acid. But also if you have electronegative atoms near it that are still pulling away electron density, that will still also increase the acidity. So they cause this polarity change. Remember, we talked about shape and polarity and how this can be affected by nearby atoms. Here's a really good example. We have ethanol and trifluoroethanol. You can see they have the exact same structure. The only difference is that these atoms here are fluorines, and on this structure, they are hydrogens. Now, none of these hydrogens or fluorines are the acidic hydrogen that we're talking about. That is this hydrogen right here. In both cases, it's connected to an oxygen, so there's no difference there. But the fluorines, being very electronegative, pull electron density on this molecule in this direction because of their shape. You can see that when you compare ethanol to trifluoroethanol, that it has this bigger region of negative electron density here and a bigger region of positive density by the proton. Ultimately, that makes the trifluoroethanol more acidic than the ethanol, and it's because of these fluorines nearby pulling. You can see that also in its pKa. Remember, pKa, the lower the pKa, the more acidic. So ethanols is 16, and trifluoroethanols is 11.3. One last factor to consider is the resonance delocalization. When you have the loss of a proton, and when that loss establishes a lone pair on the conjugate base, this can be involved in resonance delocalization, and that will stabilize the conjugate base. An acid tends to be more acidic when its conjugate base has resonance stabilization. So if the form of the conjugate base is stable when you get rid of a proton, that molecule is more likely to donate its proton if its end product is stable and is stabilized by resonance. Here we can see this is the conjugate base of acetic acid. So this is after the proton has been removed. The proton used to be right here. It was removed in a reaction, leaving this negative charge, which can rearrange in resonance stabilization with the double bond up here and go between these two products. So remember, ultimately, this is going to have a stabilization more like this, where we kind of have a partial negative charge on each of these oxygens, and they're sharing electron density between the two. They kind of go between the two equally. Ultimately, that makes this more stable. And because the conjugate base is stable, it makes the original acid more acidic, more likely to donate its proton. So let's do an example here. Based on our rules we just went over, which of the following here is the strongest acid? Now you can see that between A, B, C, and D, structurally, they're all very similar, except that we have a different element on the end: fluorine, chlorine, bromine, or iodine. Now I want you to consider the structure here. And notice that where the fluorine, chlorine, bromine, and iodine are, they are not on or connected to the hydrogen that is the acidic hydrogen. Just based on our condensed structure, we can see that they're connected to carbons. Fluorine is connected to a carbon. Remember how our condensed structures show the order of connection. They don't actually show in three-dimensional space what these look like, but they at least show the order of connection. And you can see that the fluorine is connected to a carbon and not a hydrogen. Okay, so these elements are not involved in the direct connection of the hydrogen, the proton bond. And if we go back to our factors, factors 1 and factors 2 actually both are involved in the bond, the hydrogen bond to the acid. So both of these factors are not changing in our demonstration, right? These are involved in that direct bond, but nothing has changed in the direct bond in our example. However, we are changing some of the elements in the region. They're on the other end of the molecule. And as we said with factor 3 in our inductive effects, if there are nearby electronegative atoms, the more electronegative they are, the more they can pull electron density and cause something to be more acidic. So if we keep that in mind, and we know that these end atoms, we're changing the end atoms from fluorine to chlorine to bromine to iodine. If you remember, fluorine is the most electronegative, actually most electronegative atom in general on the periodic table. And so it is going to cause the largest inductive effect, causing the molecule with fluorine on it to be the strongest acid. Now, as a reminder, if something is a stronger acid, that means that it has a large Ka and a small pKa, just to remind you. And this is from the inductive effect. Okay, so let's look at another practice. Here we're showing an equilibrium reaction. And we want to identify where the strongest acid is. And based on that, you can also identify which direction this reaction would be more favored. So here we have CH3, CH2OH, and H2SO4. Now, hopefully many of you can actually identify the acid in this reaction, but if not, I want you to look at the other side and look where protons are moving. Again, we're talking about Bronsted-Lowry, so we're talking about where protons move. And if you notice on this product side of the reaction, here's our HSO4 and H2SO4. So H2SO4 has lost a proton on the product side, and the CH3CH2OH has gained a proton. So that means that in this instance, a proton moved from here to here. And we know that the item that donates a proton is our acid, and the acceptor is the base, which means this over here is our conjugate acid, the opposite of the base. And this is our conjugate base. Okay, so we want to compare between these two, the acid and the conjugate acid of the two acids, which is the strongest acid. So here we have something that is an acid that has a proton connected to a oxygen. Just look at our condensed formula. We know that the added on proton is on the oxygen. And here we have an HS bond connected to our on our acid here. So if we want to talk about bond rules, about electronegativity and size, if you look at periodic table, the size of the sulfur is actually much larger than the oxygen. That is going to weaken this bond. So size of sulfur is larger. Now the electronegativity of oxygen is actually larger than sulfur generally. So that kind of negates that. But another factor we can think about is the inductive effect. What is around these protons? And again, just look at the formula. What else is attached here? On this acid, we have 4 oxygens. So 4 oxygens versus on this other end, we have some carbons and hydrogens. Sorry about that. Some carbons and hydrogens, okay? Now, between those two things, the one that is the most electronegative very much is the oxygens, and there are 4 of them. Okay, so this is going to cause a much stronger inductive effect. So in this case, our stronger acid is going to be the H2SO4. And because we know that H2SO4 is the stronger acid, and our conjugate acid is the weaker acid, this is the weak. We also know that that means this reaction is going to favor the direction going from the strong to the weak. So this direction.